Hello, I'm Billy Younger, and I'm here again today to help you learn some more physics. This time I'm wanting to talk to you about what a plane wave is. Specifically, we're thinking about plane waves as solutions to wave equations, and I want to give you the mathematical background for them. In other words, what does a plane wave actually look like as a mathematical equation, and or at least as a function, and then what does it mean when you have kx minus omega t versus kx plus omega t, and some other things like that. First off, you want to think about, for instance, the sound of my voice. As a person, my voice, my head is quite small compared to the area over which my voice can be heard. So I act like a point source. And what that does is, in general, it causes my voice to go out in sort of a cone. If I was really a true point source, where it's like a speaker on top of a thin pole, then it could go out spherically. But the main thing is, as it goes out, it sort of covers a semi-spherical, not complete hemispherical, but semi-spherical uh, wave front, if you will, as the sound waves go out. Now, in that case, it's actual sound wave, which is sort of like a pressure wave or a density wave, uh, because really it causes compaction and rarefactions, and they're actually moving and oscillating in the same direction. Many waves that we interact with are also, instead of longitudinal like that, they're also transverse waves. So transverse waves would be ones where they oscillate in one dimension, say, and travel in yet another perpendicular direction. So longitudinal waves travel in the same direction as they oscillate, like that. Whereas transverse waves oscillate in one direction but move in another direction. For instance, electromagnetic wave is a transverse wave. And in fact, it's an electric field that oscillates in one direction, and then a magnetic field that operates in the other direction, and then the velocity actually travels in the third mutually perpendicular direction, like this towards you. Okay, ocean waves are sort of a little bit of a mixture of transverse and longitudinal wave, and you can see this if you're actually out in the ocean and a wave starts to first pull you back, and then it lifts you up, and then brings you past, and then comes back. So you can see you're both going forward and backwards and up and down. So that's indicative of a longitudinal wave. I'm going to be working mostly with transverse waves here, just because it's easier to see the actual wave as it functions. In other words, we can talk about the actual amplitude as a function of position and time. So let me start by showing you some of the equations and what a plane wave is supposed to look like. Oh, the reason why I was talking about how the waves would actually propagate out in a semicircular space is, as that semicircular space goes out, that where the crest of that first wave, say, is, it will get flatter and flatter. In other words, the radius becomes so large that it essentially gets flat. And a flat wave really is, or a plane wave really is, a sort of a flat wave. It's a basically, there exists a plane on which the wave has a constant value, and that plane happens to be perpendicular, in that case, to the velocity that it's traveling at, the direction it's traveling in. And that's what we're going to work with now. So let me turn over to my document cam and start from there. So this is what is a plane wave. So you can look at a plane wave just like a regular sine curve. So you can say like this and this. This would be, say, the y-axis. And this would be, you could call this, for instance, the x-axis, okay? You could also call it the time axis, in which case it's, going to be moving through. But either way, the main thing is what we're going to see is a wave that reaches some maximum amplitude, comes back down, reaches a maximum negative amplitude, comes back up, reaches some maximum positive amplitude, comes back down, reaches a maximum negative amplitude, so on and so forth. Now, if it's a plane wave, this will go on. In other words, you can define a plane where this constant value, say the top of this peak, or say this little value right here, will be a constant all over that whole plane. To see that, we can actually imagine the wave going off in a direction perpendicular to that one, and show it as a full physical object. So this would be the actual wave. And it would go on, of course, for infinity this way, and it would go on for infinity this way. And that's the actual plane wave we're talking about here. So in this case, you can see, for instance, the peak of the wave would be right along that line. The trough of the wave would be along that line. The midpoint, say, of the wave would be along that line. The midpoint of the wave would be along that line. We could even go further and realize that this wave is going to block some of the vision we have of that. That's a plane wave. So this wave might, if it's a transverse wave, like I told you I was going to work on as an example, that wave might be traveling that way. And what you could do is you could say, well, y is equal to some amplitude A times the, in this case, I'm going to write sine because that looks just like sine of kx minus omega t. Okay. Now that would actually be the wave, and what I'm going to tell you is that this is a wave propagating forward, and I'll make some sense of that in a second. Of course, you can also do y equals a cosine kx minus omega t, and you could just add a phase constant if you want. And for instance, if that's chosen properly, then the cosine looks just like the sine, and that would work for this. You could also add a phase constant there. The main thing is you're solving normally a wave equation is a second order differential equation, so you'll need two constants. This one only has one A. It looks like it might have more K and omega, but you'll see that the stipulations for the actual wave equation force K and omega to have a very distinct relationship. Specifically, the relationship is the velocity of the wave has to be, and this is called the phase velocity, by the way. The phase velocity of the wave has to be the omega, the angular frequency, if you will, the radians per second, divided by k, which is the wave number. K is equal to 2 pi over lambda. So a more general solution might be y is equal to a1 sine kx minus omega t plus a2 cosine kx minus omega t. In that case, you actually have two constants, a1 and a2, so you don't really need the phase constant, but you can see it's an amalgam of the sine and the cosine. Now, the big thing is, in reality, what this kx is when the thing is traveling along, in other words, it's oscillating, its oscillations are changing along the x direction, then it's kx minus omega t. If the oscillations were changing along the y direction, it would be ky minus omega t. And if it was changing along the z direction, it'd be kz minus omega t. Or in general, the expression would be k vector dotted with r vector, where r is really the position vector that points to where you're looking at the wave. Okay. So you can see that would be k sub x, x, k sub y, y, k sub z, z, and k is defined to be 2 pi over the wavelength of the wave. And of course, omega is also equal to 2 pi times the frequency of the wave, where that just converts it to, for instance, cycles per second or hertz or something along those lines, because 2 pi radians is the number of radians in a single cycle, or a single hertz, if you will, or a single, yeah, I'll just say it that way. So anyways, that's a generalization of it. Now, if you want to see that this is in fact a wave moving to the right, and of course it's along the x-axis, I think y'all can all see that ky minus omega t would move along the y-axis, and kz minus omega t would move along the z-axis. But if you want to see that it actually moves to the right, what we do is we set this phase, and this argument here for a sinusoidal or cosinusoidal wave is called the phase. And if you set that phase equal to a constant, then it specifically talks about one point on the wave. So for instance, I could set the phase equal to pi over 2. In which case, if I'm dealing with this function, then the pi over 2 corresponds to this point right here. If it was a cosine function, then it would correspond to basically where the cosine function comes down and then hits the y-axis, or excuse me, the x-axis. That would be what happens when phi was, or when the phase was equal to pi over 2. So it's the main thing is if I set that equal to a constant, then I'm talking about one particular output for the trig function sine kx minus omega t. So when I set that, I know it points to a certain spot, which I've indicated there on the wave. Well, that's also equal to k times x minus omega t. So if I want to solve for x, because then I'd realize, okay, wait a second, this point, if I get x is moving and I can solve for x, then what I'll find out is whatever the motion of x is really the motion of the wave. So I'm going to solve this pi over 2 equals kx minus omega t for x. And I think you can see that it becomes kx equals pi over 2 plus omega t. Okay, now if you actually plug this equation, let's say this form right here, into a wave equation, the wave equation is going to force us to have v is equal to omega over k, which, as I told you before, is 2 pi times f over 2 pi times over lambda, which ends up becoming lambda times f, and that'll come in pretty handy. That's the velocity of the wave, which if we're talking about electromagnetic waves, that'd be the speed of light. If we're talking about a wave on a string, that would be the square root of the tension divided by the mass per unit length, stuff like that. But anyways, that's a set quantity. So now if I divide through by k, whatever I do to one side, of course, I must do to the other. Now I'm going to get x is equal to pi over 2 times 2 pi over lambda, because that's what the k is going to be in the bottom now. Okay. And then for the other term, omega over k, I'm going to get omega t over 2 pi over lambda. I think you can see where I'm going with this. I'm going to have to flip this denominator over and make it multiplication that way, because that's what the division by a fraction is. So I'll get pi over 2 times lambda over 2 pi. And you see the pi's cancel out, and that's ultimately going to give me lambda over 4, which makes sense because that's 1/4 of the wavelength. The wavelength would actually be from here to, say, here. And that is 1/4 of that distance. So that's how much it shifted over at t equals 0. Now the other part becomes omega, which I'm going to write as 2 pi f, and then omega times t becomes omega 2 pi f times t over 2 pi. But now you can see the lambda, which was in the bottom. I'll go ahead and show it in the bottom, and we'll work with it again in the next line. So now I'm going to go ahead and flip that 2 pi over omega over to complete the division of 2 pi ft by 2 pi over lambda. And in this case, I now get lambda over 4 plus f times lambda times t. You can see what happens is this 2 pi is going to cancel out with this 2 pi. This lambda is going to come up top, so I'll have f times lambda, which, by the way, is the same thing as lambda times f, and therefore is the velocity. So this means that the x, in other words, this point on the wave right here, is going to start off at t equals 0 at the position x equals lambda over 4, and that makes perfect sense because, like I said, this distance is lambda. It's the distance from the midline, skip 1 to the midline, or the distance from the peak to the peak, or the distance from the trough to the trough. Those are all reminiscent of the wavelength that's measured in meters or centimeters or angstroms or whatever. So we can see at t equals 0, it should be, in fact, pi over 4. And then I have plus the velocity times the time. So the velocity being a positive quantity multiplied by the time. When time is equal to 0, you get pi over 4 as we expected. But as time goes on, notice it becomes 1 second times the velocity, or 2 seconds times the velocity. So the wave is, in fact, moving this way. So kx minus omega t implies a wave propagating in the positive x direction. So that's one thing we've concluded, is that the kx minus omega t would in fact be a wave moving in the positive x direction. Similarly, you could solve kx plus omega t equals pi over 2 to get x is equal to lambda over 4. In this case, it'll be minus v times t. And you can see that obviously at t equals 0, pi over 4 would put us right here. But that point now is going to be moving to the left. So this one says moving in negative, I should write that out, negative x direction. Obviously, if it was ky minus omega t, then it'd be moving in the positive y direction. If it's ky plus omega t, it's moving in the negative y direction. If it's kz minus omega t, it's moving in the positive z direction. If it's kz plus omega t, then it's moving in the negative z direction. So that's really what plane waves are. That's how we can represent them. And that is a very typical way to show them. The only thing I should probably show you is the typical scenario. Let's say this is a wave. Let's say we're going to use the function y is equal to a cosine k x minus omega t. And let's say that d2, well, it would normally be written del squared y equals 1 over v squared second partial y with respect to time squared. But in this case, we really only have it in the x direction. So I can just write the second partial of y with respect to x squared is equal to 1 over v squared times the second partial y with respect to t squared. That's really a wave equation. That's the typical form of a wave equation. When you let y equal this function, then you say that the partial of y with respect to x is going to be a times the derivative of cosine of u. The derivative of cosine of u is negative sine. So I'm going to write negative a sine. Now it's the sine of u, which is kx minus omega t. And of course, now I've got to take the derivative of u with respect to x. So u being kx minus t, omega t, then du dt, or du dx, excuse me, would be k. So I get negative ka sine kx minus omega t. Really, I could put a plus phi in here, and I should have to make it fully general. It would apply, but don't worry about it. It's not that big a deal. Now I get the second derivative of y with respect to x squared is going to be negative k times a times the derivative of sine u times the derivative of u with respect to x. Well, the derivative of sine u is cosine u, so the sine's going to stay the same. So it'll be negative. Only derivative of u with respect to x is k, so now I've got k squared a cosine kx minus omega t. Again, this could be kx minus omega t plus some phase angle, and that would be just fine. Now we got to compute the second derivative of y with respect to t, just like we did here. And then we got to put it back in the equation, and you'll see that, in fact, in order for this to be a wave equation, the velocity has to be omega over k. So I take the partial of y with respect to t, and I get, of course, the derivative of y with respect to t. Since y is cosine, it's just going to become a times the derivative of cosine, which would be negative sine of u. Now I got to take the derivative of u with respect to t, which in this case is minus omega. So I'm going to say, make this well, I'll go ahead and write it like this, kx minus omega t. And then I'm going to say all of this is multiplied by negative omega. So in fact, it equals omega a sine kx minus omega t. Okay, notice that omega, negative omega is being multiplied by the whole thing. I just didn't leave myself enough room to do it. Now the second derivative of y with respect to t squared is going to be the derivative of this with respect to t, and the derivative of this with respect to t is clearly the derivative of sine u, and then derivative of u with respect to t. Derivative of sine u is negative cosine u, so I'll put a negative here. I'll put an omega here. I'll put an a there. Derivative of sine becomes cosine, and I get kx minus omega t again. Now the derivative of u with respect to t is negative omega. So negative omega times actually in this case I had derivative of sine was positive sine. So this one should actually come out to be a negative omega squared. So basically I took the derivative of sine, that gave me cosine. Then I had to multiply it by negative omega. That's where the negative came from. Now if I plug these back into here, what you'll see that I get is the second derivative of y with respect to time is negative k squared a cosine kx minus omega t is equal to 1 over v squared. I'll put that bigger so you can see that it's actually an exponent of 2 equal to v squared times, now I got to take the second derivative of y with respect to time. That's going to be negative omega squared a cosine kx minus omega t. Make this into a square bracket, and you can see basically if I pull them, well, actually when I pull it over here, it'll be omega, negative omega, and then come over there, it'll be a positive. So I'll get negative k squared plus omega squared over v squared, all that times a cosine kx minus omega t is equal to 0. And of course, this has to be true. This has to be true for all x and t, as the nature of the equation is. So we can consider the case where x and t does not combine to give us a 0, and we can divide through by a cosine kx minus omega t, and then you have this being equal to 0. So this being equal to 0 gives us k squared is equal to omega squared over v squared, or it gives us that v is equal to omega over k. So in order for this to truly be a solution of the wave equation, we have to have v equals omega over k. Again, defining omega as 2 pi f and k as 2 pi over lambda, you get that the 2 pi's will cancel out, and you'll get basically lambda times f is the velocity. That's it. I think that's plenty of background to show you what a plane wave is. Like I said, the general form would be k dot r minus omega t, but you can always just choose your coordinate system such that it's doing the oscillating along one particular axis, in which case it just becomes k times that axis's variable minus omega t. I hope that helps you. Have a good day.